All right, now let's talk about the properties of continuity. You're going to need to be able to not only know these, but use these. The definition of continuity on a closed interval is threefold. First, the function must be continuous on the open interval. So that's the first thing you have to show, is that it's continuous on the open interval. The next thing you need to show is that the function is continuous from the right. That is, the limit as x goes to a from the right is equal to f evaluated at a. And the third thing you need to show is that the limit as x approaches b from the left of f of x is indeed f evaluated at b. So basically, you're going to need to observe the behavior between the endpoints, and then find the value a, f at a, and b, f at b. All right? And once you've done those three things, you've shown that the function is continuous on this closed interval a, b. Let's do one. F of x is the square root of 1 minus x squared. Well, this function is, if you were to sketch this, it's a semicircle from -1 to 1. So the function is only defined between -1 and 1. So indeed, f of x is continuous on the open interval, -1 to 1. That's the first thing I need to see. You need to make that statement. All right. The second thing I need to see is you need to do the evaluation. So let's do the limit as x goes to -1, and we're going to put a little plus here, of the square root of 1 minus x squared. When I do this evaluation, is equal to 0, and this indeed is equal to f evaluated at -1. That's the second thing I need you to do. And let me do the third one in a different color. The limit as x goes to 1 from the negative, so it's this way, it's from the left, of the square root of 1 minus x squared is, indeed, that is 0, which is also f evaluated at 1. So you've shown me f is continuous on this interval. The right and left-handed limits are equal to the value of the function at those points. And now, and only now, can you state, therefore, f of x is continuous on the closed interval, -1 to 1. These are all the steps I need to see. This is exactly what I need to see on any problem. You can't just say, yes. Cutting steps of that, let's see, on a test or quiz, that'd be 1, 2, 3, at least 4 points. Probably 5 because I need to see a graph. Your turn. Pause the tape, do some notebook problems. Now let's talk about the properties of continuity. Let's say that b is some real number. It can be any number you want. For this example, let's let b equal, 3. And f and g are continuous at x equals c. So let's let f of x equal, what do you say, x plus 4? And g of x equal, I don't know, what do you want? Let's do something funky. Let's do cosine of theta. Let's do cosine of x, excuse me. And let's look at x equal 0. Or let's let c equal 0. So we're going to look at these functions evaluated when x is equal to 0. Now, the following functions are also continuous at c. Multiplying a function by a scalar constant doesn't change its continuity. So b times f is 3 times x plus 4, and by theorem 1.11, this is continuous. The sum of the two functions is also continuous. So f plus g is x plus 4 plus cosine of x. This is also continuous. The product, f times g, is x plus 4 times cosine of x. Multiplying them doesn't change the continuity of the product. Now, quotient, you have to be a little careful. All right, f divided by g is continuous if and only if g is not 0 at that point. So this would be x plus 4 divided by cosine theta, cosine x. Sorry, keep popping into theta notation. Now, at c equals 0, indeed, it is still continuous because it is not 0 in the denominator. All right, your turn. Turn off the tape. Now, let's look at composite functions. Composite functions are a lot of fun. They really are. Mathematicians love playing with composite functions. All right, let's say g is continuous at c and f is continuous at g of c. Then the composite function f of g of x, or f evaluated at g of x, is also continuous at c. All right, let's look at our example here. When f was x plus 4 and g, let's call it cosine. All right, and let's look at c equals 0. These functions are both continuous at c equals 0. So f of g of x means everywhere in f, where you see an x, you're going to plug in g of x. So everywhere I have an x in f, I'm going to plug in a g. So this is f, and I'm going to, oops, I didn't want that. Sorry about that. This is g plus 4. I'm putting in the step even though you don't really need it. So it's cosine x plus 4. This function is still continuous at c. Now let's do g of f of x. Golf. All right, I'm going to write the function g, and that's cosine, and everywhere I have an x, I'm going to put in an f. So I'm just going to put the f here, and I'm going to rewrite it. So this is cosine of x plus 4. This is also continuous. Both of these are continuous. Now, you don't have to show me this step right here. I just did it for an example. All right. Now, notebook problems. Quite a number of them, I know. All right. When you're done, turn off the tape and finish your homework.